wait a minute, because I'm going to introduce you first. Okay.
Sure.
Bueno, buenas tardes, después de todos los problemitas. Le damos la bienvenida al doctor Kaustubh Hakim, que nos dará una charla de manera remota desde Bélgica, y así que, bueno, también eso introduce unas cuantas cuestiones extras. Así que, well, thank you very much, Kaustubh, for accepting our invitation and considering that for you it's 7 p.m. in the evening, so, and with 40 degrees, for us it's very cold. So, well, I'm going to introduce you in Spanish. Dr. Hakim es un apasionado de comprender la química de los exoplanetas. Actualmente es investigador de la Universidad Católica de Leuven y del Observatorio Real de Bélgica. Entre el 2019 y el 2023 realizó un postdoctorado de larga duración en la Universidad de Berna. Previamente obtuvo un doctorado en astrofísica y geoquímica realizado conjuntamente entre la Universidad de Ámsterdam y la Vrije Universiteit Amsterdam, perdón, mi alemán. También completó una maestría en astronomía en la KU Leuven. Antes de dedicarse a la astronomía, trabajó durante un par de años en un banco de inversión en Mumbai y obtuvo una licenciatura en ingeniería electrónica en el Instituto Indio de Tecnología de Kharagpur. Thank you, Kaustubh, and you can start now.
Okay. Hola a todos. Buenas tardes. That is my Spanish. So I will switch to English now. So thanks everyone for joining this talk. Yeah, and thank you very much, Mariela, for inviting me to something. Actually, most of you don't think on a daily basis. So I'll try to do my best to cover all the different backgrounds in this topic, and then also try to dive a bit deeper into my own research towards the end of the colloquium. Okay, so I'm going to planets. So here, what small exoplanets also talk about to different disciplines coming together, understand. Okay. In this animation, which is already very old now, it's from 2011, what you can see is different planetary systems and what the rotating planets are rotating around the star, but the star is not shown in this animation. But what is important to realize is there are some dashed lines here. So the dashed lines for the innermost four are for Mercury, Venus, Earth, and Mars. And then this is for Jupiter and then Saturn. So this is the scale of solar system. So solar system is quite wide in terms of orbital separation of planets, but the planets which have been detected until now, most of them are in very tight orbits. Most exoplanets we know, you see here, are orbiting closer than where Mercury is orbiting around the sun. That's one immediately take up. Is the size of, so the smaller the size, the smaller the planet, and the bigger the size of this disk, the bigger the planet. So the planets really range from Mercury size to larger than Jupiter. Another kind of information is the temperature at the top of the atmosphere. We call it the planet equilibrium temperature. Technically, it is independent of the atmospheric temperature, but it gives us an idea of how strongly irradiated the planet is. And these planets can be very cool, much cooler than Earth, but Others could be very, very hot. So you can see some red spinning dots. So these have atmospheric temperatures of higher than 1000 Kelvin. Okay, so let me start again here. So what is also important is how do we learn about these different exoplanets? On the top left, you see a method called direct imaging. One would expect, just like imaging stars, one can image exoplanets, but of course, the contrast, the brightness contrast between the star and the planet is very large. And because of that, it's important to block the host star's light in order to see the planets. And this is being done here on the top left animation for a planetary system called HRH 799. And it has 4 Jupiter mass exoplanets. And this method, although one would think could be a common method, but it's a very difficult method observationally. So most exoplanets are not detected by direct imaging. On the top right, you see a method. It's called Doppler spectroscopy or radial velocimetry. And because of the gravitational pull of the planet around the star, the stellar light sometimes shifts leftward, meaning blue shifted, or to the right, which is red shifted. And because of this, one can estimate the minimum mass of the planet. At the bottom left is one of the most successful methods in detecting exoplanets. Is called transit photometry. Yeah, I have some lag in the animations and transitions. So in transit photometry, the stellar light is blocked by the transiting planet, and the area which it blocks is proportional to the ratio of the radius of the planet divided by star squared. And this is the way we know the radii of exoplanets. And then there is a method called transit spectroscopy, which really allows us to characterize the atmospheres of exoplanets. In transit spectroscopy, what happens is the same configuration as transit photometry, but now we analyze this light in different wavelengths. And for example, the configuration where the planet is in front of the star, the transit, we call this transmission spectroscopy. And during this time, the light passes through the atmosphere of the planet and reaches us. And this is the way we try to understand what the atmospheres contain. And then there is also what we call the day-side emission spectroscopy. So when planet emerges just behind the star, it also shines light or reflected from, and we also allows us to study the atmospheres. And besides that, there is also phase curve spectroscopy, which is nothing but phases in between, which also allow us to study this in detail. And of course, you must have already heard that physics prize in 2019 was awarded to Didier Queloz and Michel Mayor for their 1995 discovery of the first exoplanet around a solar-like star, which is called 51 Peg-B, and it was discovered using the radial velocimetry method. And of course, since then, all these methods combined are giving us a lot of information about different kinds of exoplanets. So Kepler space mission was a very important space mission which retired, and it gave us boost in exoplanet population. It hunted for thousands of exoplanets, but now it's not operational. But what is operational now are missions like TESS and Cheops, which keep hunting for new exoplanets. And with James Webb Space Telescope, there is characterization of atmosphere, ground-based techniques, especially with a very large telescope, which allow us to study the atmosphere, albeit in a very narrow band. I would also like to highlight one telescope array we are building with a KU Leuven-led consortium. This is a European, mostly European consortium, but also partners in Australia. And we will be able to do radial velocimetry. The minimum mass. PLATO launched. European Space Agency is scheduling for early next year now. The expectations are this will detect habitable zone exoplanets around sun-like stars. So it will also increase the number of detections, and we expect to go to wider orbital separations than what you saw in the first animation I showed you. Besides that, Ariel Space Telescope will be a dedicated exoplanet atmospheric characterizing mission. And from the ground, we obviously know that extremely large telescope will do a lot of fantastic astronomy, but also great exoplanet science with instruments such as METIS and ANDIS. Beyond this, there are discussions like Habitable Worlds Observatory and large interferometer for Earth-like exoplanets. And the idea is to really try to detect the atmospheric composition of Earth-like planets around sun-like stars with those missions. If they become live, this will be already only in 2040s, not before that. Of course, this is not an exhaustive list of all the missions. I just picked a few to highlight the diversity of observations in exoplanet science. So what all these missions give us is things like radius, mass, atmospheric composition, and also imaging. And that's why we need different ways, different observational techniques, because they tell us something different about the exoplanet. Okay, so in 1995, we had an exoplanet around sun-like star, but since 1995, things changed. So what you can see in this plot is the planet occurrence frequency diagram as a function of planet radius. So Earth is here, Neptune is here, and Jupiter is here. And these three are to scale with each other. What is the biggest discovery during the last 30 years is we see a huge population of exoplanets between Earth and Neptune. Now I'm trying to see why this animation is not running in this mode. But let me use the next plot to just give you the same information. So what we know now is exoplanets between the size of Earth and Neptune are the most common exoplanets in our galaxy. And this is a big surprise because no one thought that most exoplanets would be here. Because from the solar system, we know that there are 4 rocky planets and 4 gas or ice giants, and nothing in between. And it seems like most of the planets in the galaxy are in between. What this plot also shows is as a function of age, the distribution changes. So on the left are these what we call the super Earths, and on the right are these sub-Neptunes. But if you look at younger planets, the population of sub-Neptunes is larger than that of rocky planets. Furthermore, if you look at the older planets, the population of super Earths is almost the same as sub-Neptunes. And as you go to older planets, the population of planets larger than Neptune further decreases. What this potentially tells us is there is atmospheric mass loss, especially for sub-Neptunes, and most of quite a large fraction of them lose their atmospheres and become rocky because there is no hydrogen helium rich atmosphere anymore. So in fact, correcting for observational bias, suggestions are that most of the planets, meaning more than 95% of the exoplanets in the galaxy, are small, that is smaller than Neptune, and really between the size of Earth and Neptune. So what does this really mean for planet formation? This is a big puzzle because previous planet formation models expected solar system like planetary systems. You have rocky planets in the inner solar system and gaseous planets further away. But of course, now because we have to explain these more than 95% of planets, two theories have become more popular. There are many different models and many different tweaks, but on the left, you see something we call the embryo migration model. This is in some sense more classic planet formation model, that planets grow outside the snow line. So this is the orbital distance from the star where ice can condense, water can condense as ice. And because now ice can also be part of embryos, they can keep this ice once they migrate inward. And that's how you produce volatile rich planets. So this embryo migration model favors volatile rich planets. But since more than a decade, almost 2 decades, there is another discussion of pebble drift. And what pebble drift model suggests is, instead of starting with embryos, most of these building blocks starts with pebbles. And because pebbles, once they cross the snow line, they can lose the ice. And because of that, the final product, the planets which form from dry pebbles, are also dry. They are volatile poor. So these are the two competing theories of small planets, what their composition could be. What this also means that if through observations we can get a good handle on what is the volatile content of small exoplanets, we can also say something about planet formation and evolution, which theories are really important, or which theories can be ruled out potentially. So in exoplanet science, this is my personal biased view. So these are the three big questions I think there are. One is, are exoplanets habitable? And of course, this is driving all these new concept missions for 2040s and 2050s, where else we can find life. But of course, a fundamental question is, what is the nature of exoplanets? Now you saw from the plots I showed, most planets are in between the size of Earth and Neptune. So are they just like Earth, or are they just smaller versions of Neptune? Or are they something completely different that we cannot even imagine? And of course, this connects also to how the planets form and evolve. And this is also something I partly alluded to in the previous slide. In the presentation going forward, I will specifically focus on this question: what is the composition of small exoplanets? So let's take a look at our basic information, what we get for exoplanets. So as I said, the most basic information we can get is mass and radius. And because mass and radius give us bulk density, we have an idea about the bulk composition. What you see in this mass radius diagram is all these gray dots are observed exoplanets, and all these solid lines are theoretical models of spheres of iron, rock, water, and hydrogen. What we can immediately notice is there is a big blob of observed planets close to a hydrogen line. So this tells us that these planets are mostly made of hydrogen, hydrogen being one of the lightest components which makes planets. And therefore, they are most likely like Jupiter and Saturn in overall composition. If you look at the planets really at the bottom, these planets around the green line, which is the rock line, it's for composition of rocks, these planets also most likely have an Earth-like composition overall, or we can say rocky planet-like composition like we see in the solar system. The planets in between, though, which again, these are the rocky planets, sub-Neptunes and gas giants. So the sub-Neptunes, they similar masses, they range quite a bit in radii. So some of them are very dense, can have compositions close to rocks, but others are very light, and their composition could be in between that of hydrogen and water. So of course, this new class of exoplanet sub-Neptunes is even more intriguing in terms of what its composition is like. So to scale, if we draw what is the how the rocky worlds are like, they have very, very thin atmospheres which do not contain hydrogen helium. But then there are gas giants which have a very small rocky core and mostly hydrogen helium gas in them. And then the sub-Neptunes are in between. So if we ballpark try to estimate what is the rock to gas ratio. So assuming rock forms the interior and gas forms the atmosphere, we can say that rocky worlds have less than 0.01% of gas. Gas giants are more than 90% of gas, while sub-Neptunes are in between. They are between 0.01 to 10% gas. And of course, this is also, this spans 3 orders of magnitude. So although this mass radius information gives us some insight into composition, but it is not conclusive enough to say more, especially about sub-Neptunes. So one of the things recently has come up in exoplanet science, the discussion of interior atmosphere interactions. And I would like to go into detail into this and throughout my talk, and I will explain what I mean by that. But first, take a look at the James Webb Space Telescope's data. So what you see are atmospheric spectra. So as a function of wavelength, you see for 5 exoplanets here. And for the top one, the green, there has been detection of water vapor in this exoplanet. On the bottom one, there are tentative water vapor. And the other two, however, little or no water vapor. They are mostly rich in carbon-bearing molecules like CH4, CO2, and so on. So what all of this is telling us already is there is quite a big atmospheric diversity. Already with 4 type of planets, we see some diversity. And as more data comes, this diversity might also increase. Nevertheless, what this means is we can detect all these different molecules like H2O, CH4 at hundreds of parts per million levels, because they have a very good background hydrogen helium atmosphere, which provides a good atmospheric scale height to detect these molecules. For rocky planets, because they do not have these hydrogen helium atmosphere, detection of other molecules becomes even more difficult, and that's also been discovered not only for this planet, but there have been a few others, like the TRAPPIST-1 planets, where there is no conclusive evidence of what is the composition of their atmosphere, or if they even have an atmosphere. So for me, what is very interesting is what these sub-Neptunes are made of, because these are unlike any atmospheres we have seen in the solar system. So then the specific question to be asked is, what is the composition of deeper layers of sub-Neptunes? So this is something we can detect carbon-bearing molecules in the uppermost atmosphere, which has a mass. The uppermost layer has a negligible mass compared to planetary mass. So it is still not clear what is the composition of deeper atmosphere and the rocky interior of sub-Neptunes. So this is again to summarize what are the different possible deep atmosphere and interior compositions. On the top left, you see a possibility of condensed water layer on top of a solid interior. And this is extension of what we understand from Earth, that Earth has a more or less solid interior and there is a water ocean on top of it. But here the water ocean would be really large, and it won't be covered by oxygen, nitrogen bearing atmosphere. It will be covered by a hydrogen helium rich atmosphere. On the right, there is a scenario where water vapor, condensed water layer cannot exist as a separate phase. It forms a supercritical fluid with hydrogen. On the bottom right, there is a possibility that there is a liquid rocky interior, which we call magma oceans. So magma oceans are known to dissolve gases from the atmosphere. So of course, this is another scenario which can be possible. And on the right is a scenario where different compositions can mix together. Also, even the liquid magma and iron can maybe form a single compositional layer. So of course, you can understand from this is based on mass, radius, and atmospheric data, all these possibilities still exist. We cannot rule out these possibilities yet. So how do we go forward from here? So one of the things, one of the reasons why this is there is also because we have limited understanding of sub-Neptunes, because there is very little data, especially laboratory data, to understand what happens at very high pressures, very high temperatures, at compositions which are unique to sub-Neptunes. So these compositions do not exist in Earth or in Jupiter. So we have to invoke new composition, temperature and pressure parameter space. Another coupled importance to this is because these sub-Neptunes have different pressures, temperatures, compositions, they can also invoke some interior atmosphere coupling, which we do not fully understand yet. Okay, so to address this, first try to understand what we know. So what we know about the diversity of rocky interiors. So let's take a look at the solar system first. If we look at the solar system, there is Earth here, then Mars, Mercury, and Moon. The ratio of Earth's core to its mantle is the same ratio which exists in Mars. But Mars is 10 times lower in mass. It has only 10% of the mass of Earth. While Moon has almost non-existent core, and it's even less massive. But Mercury, on the other hand, it has a very large core relative to the mantle. And in some sense, Moon and Mercury are end members in terms of the diversity of core size. But regardless, what we understand from the inner solar system is there is an iron-rich core, and a silicate-rich mantle. So when we talk about super Earths, so now this is already a bit outdated because um, um, there have been some lab experiments at higher pressures now. But regardless, at the time when we did this study, there was information of lab experiments only until the pressure of 0.3 terapascal, which is 3 megabars. So this is the pressure at the center of Earth. And we have data but beyond there used to be extra before our study. Because we require equations of state at really, really high pressures, up to the pressures of 10 terapascal, so 100 megabar. These could be the pressures in the center of super Earths. So what we did is develop a density functional theory based equation of state. So these are ab initio calculations, quantum mechanical calculations one can do. And with this equation of state, we showed, so the horizontal line is the equation of state we have compared with the previous extrapolations. And we demonstrated that previous extrapolations were leading to density differences of up to 20%. And of course, these density differences also create uncertainties in the mass radius relations, depending on just the choice of the equation of state. And this is what is shown here is for a given radius, there could be up to 20% of difference in its mass just by changing the equation of state. Hence, here we advocated the necessity to go for ab initio simulations whenever possible instead of extrapolating low pressure data. And of course, since then, there have been some new lab experiments where now there is some data in this range, which certainly helps to model these interiors. Now we talked about physical diversity in terms of core to mantle ratio. Now let's take a look at chemical diversity. So when we think about chemical diversity, we have to understand how planets form. So planets and the host star form from the same cloud of dust and gas. And because of that, the refractory elements which forms the solids, they also go in the star. So because the planet formation happens and volatiles are lost, refractory elements are the ones that remain. And because of that, we expect the refractory element ratios like magnesium, they should reflect the same or similar ratio as in the star's photosphere as in the planet's rocky interior. Of course, from solar system, we know that these are not exact one-to-one correlations because the planet formation and evolution process for each planet could take a different pathway, and this could result in different ratios. But still, at a statistical level, something like this still holds. And this has been a discussion of studies recently. Now let's take a look at another ratio, carbon to oxygen. Like in stellar astrophysics, carbon to oxygen ratio has also importance for planetary compositions. Because once, so again, just this star is the sun and all other dots are the observed stars in solar neighborhood. So a carbon to oxygen ratio, one can generate dust which is rich in carbon bearing material like graphite and carbides. And of course, this is relatively small population, but still a significant population. And one of the interests I had was to look into what kind of composition these planets will have in the end, forming from a disk which is rich in carbides and graphite. So for this purpose, I perform laboratory experiments, and one can perform laboratory experiments in a labs. These labs are geochemistry labs. We specifically call this field experimental petrology. This is nothing but we can mix compositional recreate exoplanet composition, and this is what I am showing here with sample preparation. Once your synthetic exoplanet sample is created, one can do high pressure temperature experiments, such as with this machine, which is a hydraulic press, and the sample is really tiny. It's just 2 millimeter wide. And it sits at the center of this press, and at high pressures and temperatures, we can perform reactions which would happen only in planetary interiors. And once the experiment is done, we analyze these experiments with electron microprobe. So it's just an electron microscope where we can do quantitative analysis of which elements are present in the sample. And this is an image of one of the samples where the scale is very tiny. It's 10 micrometers. So we are really zooming in into the sample, and then what is the composition we see. And we could claim that, okay, there is this blue region, which is Leuven, then region, which is so if you remember, I was talking about silicates and iron alloys. So this is exactly what we have. These are silicates and these are iron alloys. So iron alloys, because they are very dense, they of the planet and form alloy core, and then there is a silicate mantle around it. But what we found in carbon-rich experiments is also graphite. And this graphite, although small amounts of it dissolves in the silicate melt and in the iron alloys, most of it stays as a separate phase. And of course, this would mean, because graphite is even low density compared to silicates, so it would float on top of the silicate. So you get your carbon-rich planet, which has an iron core, silicate mantle, and a graphite outer shell. So this is another illustration of the experiment. So this is the sample which you can hold in your hand. So this is 1 centimeter wide. And then we introduce it into a sample. And this sample is then zoomed in by 100 times here. And all these red regions are iron alloys and the blue regions are silicates. And if you zoom it even 1,000 times, you see this. Okay, so are these the only type of experiments we can do connected to planetary interiors? No. So we can go to even higher pressures. With piston cylinders, we can go to 4 gigapascals, where 1 gigapascal is 10 kilobars. So this is 40 kilobars. So we can go to 150 kilobars. It is also at KU Leuven. And then we can also do what we call the diamond anvil cell experiments. Some of you might have heard about these. With these, you can go to pressures of 100 to 200 gigapascals, which is 1-2 megabars. And of course, there are also other type of experiments like shock wave compression experiments, where you can go even to pressures of 1 terapascal. Well, of course, now I will stop with the experiments. Let's now think about the chemical diversity of exoplanets again. So from solar system, we know there is iron alloys, there are silicates, right? But we should keep our minds open about what other type of exoplanets can exist. And this includes possibilities of a really large amount of water, of the order of 10 weight%. So this is not like a water ocean. This is 100 to 1,000 times larger than what we have on Earth. There could also be silicate compositions which are different in the sense calcium and aluminum rich compositions. They also exhibit low density, and it has been shown some stars have calcium and aluminum. So potentially the planets forming will be much more calcium aluminum in the solar system. Example of carbon exist. Now we understood about rocky interiors, their physical diversity and chemical diversity. Now let's talk about interior atmosphere interactions. So what do I mean by interior atmosphere interactions? So on the left is one process called outgassing, or simply volcanism for this context. So what you see here is a picture of Mount Etna in Italy, and it outgasses a lot of different gases, including sulfur dioxide, for example. So all of these gases contribute to the atmosphere's composition. Then there is geochemical cycling, which is very specific to Earth and plate tectonics, where carbon dioxide is cycled from the atmosphere to the interior. But then there are also interactions when the interior becomes liquid, magma. So between the magma oceans and the atmosphere, what can happen is some of the gases in the atmosphere can dissolve in the magma, but also some of the refractory components in the magma can vaporize into the atmosphere. So what is also important is we understand interior properties in a way that we can constrain the atmospheric composition. So if we understand the coupling between interior and atmosphere better, we can also explain some of the observations that James Webb is doing with for the atmospheric composition of small exoplanets. So now I will go a little bit deep into one of the topics which interests me a lot since last few years. So these sub-Neptunes can have liquid interiors or magma oceans for billions of years. This means the sub-Neptunes we are looking at today, they can actually host a magma ocean in the deep interior. And this is because there is a very specific gas to rock ratio of sub-Neptunes. They have a lot of accretionary heat from the time of formation, and because they have a very thick hydrogen helium atmosphere, very prone to storing the heat in the interior and not letting it out to the space. And because of this reason, can, for example, Earth's magma ocean less than 1. So this is 3 orders of magnitude difference. Does is scenario talked about, where in recent studies, helium-rich atmosphere or envelope can dissolve partially in the magma. So some of these gases can be stored in the interior, rocky interior of these planets. What is also important is because the pressures are very high, there are a lot of non-ideal effects, and these also need to be taken into account in modeling. And furthermore, magma can also vaporize and pollute the envelope or the atmosphere. What has come out over the years on this is there are few molecules, especially silicon bearing, like silane and silicon monoxide, which are specifically produced only if you have a magma ocean. And if this is the case, if one would detect these gases, that would potentially say something about the presence of magma oceans. And indeed, these gases are observable in the infrared, potentially with James Webb Space Telescope, because they have signatures or lines around 5, 6, and 4 microns. Okay, so now I wanted to build a model of how the hydrogen-helium atmosphere reacts with the bulk of the rocky interior. And we did this with a newly developed tool called AtModeler, where we can self-consistently calculate chemical thermodynamics based compositions of atmosphere and interior. So this includes reactions between gases, but also the magma and gases, solubility of gases in the magma, and the non-ideal or the real gas behavior. What we also realized in this process is there is a lack of thermochemical data for the pressures, temperatures, compositions we need. And this is exactly I talked about earlier. So we had to increase of the low pressure data. Silane is with hydrogen from that, and what we provided state, non-ideal equation of state for the first time for silane or silane. And this plot just shows you the compressibility from our model matches very compressibility. So we just validated this with a new lab. Once now these equation of state, we could changes. So at the bottom you see a plot. Only ideal gases are assumed. So there is no deviation from ideality assumed. But on the top, we use all real gas equations of state. And what you can immediately see that the red line, which is silane at the bottom, which is the second after the most when you equation of state. And this is important because this enhances the amount of silicon present in the atmosphere and makes it potentially detectable. One thing to keep in mind is this is the composition and the really deep layer of atmosphere very close to its interior. Of course, the composition changes as a function of atmospheric height. But nevertheless, why very behavior, and that's why you see pronounced effect. Another effect of including real gases is the storage of hydrogen in the interior increases in the real gas models compared to ideal gas models. So we think that this is really important to keep in mind that real gases can really push for more hydrogen in the interior. We also expanded the chemical system to include carbon, nitrogen, and helium. And I will skip this in the interest of time. What we incorporate really allows us to also predict the composition of other molecules like carbon-bearing, nitrogen-bearing molecules. What is the most important takeaway from the magma atmosphere or interior coupling is the elemental ratios available in the atmosphere change because some of the elements get stored in the interior and others vaporize from the magma into the atmosphere. And this is what this plot shows. So if there was no coupling with the magma, we would see just flat lines with different colors. But you can see some trends with colors. So as the magma ocean percentage, which I call mantle melt percentage, So here on the right, you have a global magma ocean. On the left, you have a partial magma ocean. So as you go from partial to global magma ocean, the amount of silicon increases. And the amount of green is nitrogen, amount of nitrogen decreases. So this tells us that nitrogen preferentially gets stored in the interior, and silicon gets vaporized in the atmosphere. So these are the things which will change the resulting atmospheric composition. And this is what we show here for a specific TOI42. And this sub-Neptune analyzed Webb of this shows us their CO and CO, carbon in the atmosphere. What we show is indeed this can explain the observation, the presence of magma, but when we include the models with magma, partial magma oceans, this still explains the observed water vapor and carbon monoxide ratios. So in some sense, partial magma ocean interior is still consistent with observations. What we also found in this process is silicon to carbon ratio provides a diagnostic of accreted gas metallicity and magma oceans. So when you accrete more and more metals in the gas, in the sense of carbon, nitrogen, you can see the signature in the carbon, abundance of carbon. But the silicon abundance comes mostly from magma, because silicon cannot be present in such large amounts in the nebular gas or even in the metal enhanced nebular gas. And that is why we propose silicon to carbon ratio as a diagnostic for magma oceans and accreted gas metallicity, because silicon comes from magma and carbon comes from your nebular gas. So to summarize, understanding planet formation requires the knowledge of composition of small exoplanets. That's why we are researching this field of exoplanet science. Silicon to carbon ratio seems to be a great diagnostic of magma oceans and the accreted gas metallicity. And interior atmosphere interactions lead to enhancements of some of these chemical ratios. What is also important is new thermochemical data is uh, uh, needed from lab experiments and ab initio simulations. With that, I would like to thank you, and I'm open for questions.
Thank you, Hakim, for your talk. Now we have some time for questions. ¿Alguien tiene alguna pregunta? ¿Online hay alguna pregunta? We don't have any questions. Okay, thank you again, Kaustubh.
Thank you for listening.
I'm sorry for all the problems with the technical problem we had.
No issues. Okay. Have a good time,
Thank you.
everyone.
Thank you. Bye bye.